If you've ever looked up at the sky and asked questions, then you're an astronomer. You're doing something people have done for thousands of years. Many say that astronomy is the oldest of the sciences, an attempt to explain the nature and the movements of the stars. And few areas of science can show us more clearly just how radically our ideas and our understanding can change over time.
The sun rises and sets every day like clockwork. But how do we know whether it's the sun that's circling around the Earth or the Earth itself that's rotating? From here on Earth, visually, both would look exactly the same.
It's not just the sun that moves either. Take the night sky. Like the sun, the moon rises and sets. And if we look at the stars, they all too appear to move, rotating around a single point. Again, there are two possible explanations. Either the stars or the Earth itself must be moving.
For the ancient Greeks, the answer was simple. The sun and stars had to be moving, not the Earth. If the Earth was moving, wouldn't we feel it moving? The ancient Greeks therefore built a model to describe their understanding of the way the heavens moved. They placed the Earth at the centre, with the moon and the sun orbiting around. And the stars were fixed to a distant celestial sphere, itself rotating around the Earth. Everything moved in perfect circles, a symbol of the God's perfection.
But there was a problem with this system. In Greek, they called them planetos, meaning wanderers. These objects moved back and forth across the night sky. They didn't cooperate. They didn't fit the model.
To account for these wandering stars, the Greek model had to be modified. Convinced that the heavens moved in perfect circles with a fixed Earth at the centre, astronomers developed ever more complex models to account for what they saw. Circles upon circles upon circles.
But then there came an alternative model. A model proposed in the 16th century by the Polish astronomer Nicholas Copernicus and later perfected by the German Johannes Kepler, placed the sun and not the Earth at the centre.
Here I have the Sun, Earth and Mars, with the Sun at the centre of the solar system and the Earth and Mars orbiting around it. Now, if I was on Earth and I took photos of Mars night after night against a background of fixed stars, let me show you what you'd see.
We see just what the ancient astronomers saw. Mars moves forwards and backwards across the sky. The planet does not really change direction. It is simply how we view it from the Earth against a background of stars. Those wandering objects we now know were not stars themselves, but planets. And this elegant, sun-centered solution could explain away the need for the old model's never-ending circles. Then, in 17th century Italy, the astronomer Galileo Galilei did something unprecedented. He built a telescope and he pointed it at the night sky. One of the many groundbreaking discoveries that Galileo made with his telescopes was that the planet Jupiter appeared to be host to 4 moons of its own. The first direct evidence that not everything revolved around the Earth. Our place in the cosmos was no longer special. In this new model, the planets orbited around the Sun. And this meant for the Sun and stars to move across the sky, the Earth must be rotating. Here is a clear example of how science works. Scientists use models that can explain what we see and experience, models that can predict how things will behave in the future. If a new model can better explain what we see, then it replaces the old. Of course, we've come a long way since Galileo first pointed his telescope. Nowadays, they've grown a little bigger. Telescopes like the Liverpool Robotic Telescope and the giant William Herschel Telescope, located alongside many others on the island of La Palma in the Canary Islands, high above most of the clouds. With telescopes like these, the planets that caused the Greeks so much trouble are revealed in all their wondrous beauty. We can now see them in glorious detail. We now know that some of those pinpricks of light we see are not planets or stars, but entire galaxies, each made up of billions of stars, and that we are just one of billions of such galaxies stretching across a cosmos that is larger than the ancients could have ever imagined. We've put telescopes into space, giving us a new perspective on the universe. We've sent probes to other planets and even observed the sunset on Mars.
Better tools means better evidence, and this helps us develop better theories of how the universe works. The oldest of the sciences has come of age, and there's never been a better time to be an astronomer. Of course, there are some people who say that what we have learned has shown us that we and our planet are insignificant on the vast scale of the cosmos, but as far as we know, we're the only planet that's trying to understand how the universe works, and for me, that makes us special.
Here's a simple demonstration that can help show how the intensity of light varies with the angle of inclination. This is the reason why it's hotter near the equator and colder near the poles. By wrapping a cardboard cylinder around a lamp, you can create a roughly parallel beam of light that can be aimed at a piece of white card or small whiteboard held upright in front of the lamp. This should create a clearly defined circle of bright light, which you can draw around with a pen. By tilting the board backwards, you'll notice that the light spreads out into an ellipse, and the light is also not as bright as before. By drawing around the ellipse in a different colour, you can compare it with the size of the original circle. The area of the ellipse when the board is tilted is clearly larger than the area of the circle. The same amount of light is spread out over a larger area, demonstrating that the intensity of light is not as great. This helps illustrate how the latitude of a location on the Earth can affect the intensity of light it receives from the Sun per unit area, and therefore the surface temperature in that region. At the poles, the Sun's light is spread out over a wider area than at the equator, and therefore the temperature is cooler. Using a globe and a strip of thermochromic paper, you can further demonstrate the effect of inclination to show how temperature varies with location. This can show pupils how the change of temperature with the seasons is due to the axial tilt of the Earth, not, as is a common misconception, because the Earth is closer to the Sun in summer. You'll need to stick a strip of the thermochromic paper onto your globe, next to the area you're interested in, and point it towards a bulb that represents the Sun. The bulb should be positioned at the same level as the area on the globe that you are interested in. Here, the UK is in its summer position, and you should see the paper heat up from black through red to blue. Counterintuitively, in this case, blue is the hottest. 6 months later, the Earth will be on the opposite side of the Sun. The Earth is now tilted in a different direction relative to the Sun. It will now be winter in the UK. You can represent this new position by turning the whole globe 180 degrees. This means that the stand will be on the opposite side from your light source. Then spin the globe so the UK is back in its daytime position facing the sun. In the winter position with the UK higher on the globe, the paper next to the UK should not become as hot. Now, with the UK at a higher angle, the light is spread out over a larger area, so the intensity of light is less, hence why it's cooler in the winter. The phases of the moon are a consequence of the fact that the moon orbits around the Earth, and this means over the course of a month we can see different portions of the moon's sunlit side. It has nothing to do with the Earth casting its shadow onto the moon, as is a common misconception among students. Here's a way to demonstrate the phases. The sun is very large and distant compared to the moon. Therefore, we've used 3 closely spaced table lamps wrapped in cardboard cylinders to light our moon with nearly parallel beams of light. One student represents the Earth while another operates the moon, a ping-pong ball on the end of a stick. By moving the moon anti-clockwise around the Earth can observe the different phases of the moon: a new moon, a waxing crescent, half moon, waxing gibbous, and full moon, and then the waning phases. Students could take turns being the Earth, or alternatively, students could use a webcam or camera to show the rest of the class. Here's a way to demonstrate solar eclipses. The sun is very large and distant compared to the moon. Therefore, we've used 3 closely spaced table lamps wrapped in cardboard cylinders to light our moon with nearly parallel beams of light. One pupil can represent the Earth, and the moon and its orbit can be represented by a ball fixed to a hula hoop. By holding the hoop at an angle, you can demonstrate that the moon's orbit is tilted at about 5 degrees compared to the Earth's orbit. Most of the time, the moon will not line up exactly with the Earth and Sun, so usually the moon cannot be in a position to block out the Sun. The moon appears either above or below the Sun, and its shadow does not fall on the Earth. But occasionally, the Earth will be at a place during its orbit where the moon's orbital inclination allows it to pass directly between the Earth and the Sun. It is only when positioned here that the moon will completely block out the Sun, and that is when we see a solar eclipse.